Every time you log into your Tarleton student portal, check your bank balance, or stream the newest album on Spotify, you're interacting with the database. But stop and think. How do these massive systems know exactly where to find your unique record among billions? Did you know that the entire digital world doesn't run on magic, it runs on structure?
It absolutely relies on structure,
Yeah.
yeah. And, mastering that structure is really what separates a functioning system from just chaos. So today we're diving deep into the foundational language of that structure, conceptual modeling, specifically using the entity relationship or ER model. For those of you tackling database theory in practice, BCIS 4.0.1, this is basically your blueprint. It's the crucial step that bridges those abstract business requirements, like what does the organization actually need to do with the concrete functional database schema, how the computer stores the data.
Okay, let's unpack this blueprint then. Our mission here is pretty critical. We need to transform those sometimes intimidating academic concepts, entities, cardinality, constraints, into knowledge you can actually use immediately in a career setting. We've got a stack of sources that guide us through this whole design journey, really from the moment a business idea sparks all the way to the final implementation. Our goal is to make sure you can look at the mini world of any operation, whether it's, say, a logistics company or a university registrar, and translate it into a sound, accurate conceptual model.
Right. And conceptual modeling is, I'd argue, probably the most important and non-technical skill you learn in this field. It's what ensures that the technical solution actually solves the real business problem. So look, if you find this deep dive useful for prepping for class or just solidifying your understanding of how data architecture really works, make sure to follow the show. And definitely check the description for supplementary materials, links to the notations we'll talk about, and those crucial case studies we're about to break down. This is foundational knowledge, that's KO1, and it leads directly to marketable design skills, which is SO2.
Okay, so let's start right at the beginning. Why do we spend so much time drawing, boxes and diamonds and lines before we even touch a keyboard or write a single line of SQL? What exactly is conceptual design, and where does it fit into the whole database design timeline?
Right. Conceptual design is the absolute first phase of database design. It comes immediately after you've done a really comprehensive analysis of user and business requirements. Its primary characteristic, the thing that makes it distinct, is that it is high level and crucially independent of all physical considerations. That independence is absolutely key.
Wait, why is that independence so critical? I mean, if I already know I'm going to use, say, Microsoft SQL Server, why shouldn't I just design the model specifically for that from the get-go?
Good question. Because a good conceptual model needs to outlive the specific technology you choose today. If you start baking implementation details in too early during the conceptual phase, you seriously limit your flexibility down the road. At this stage, we honestly don't care if we're using Oracle or PostgreSQL or even something like MongoDB. We don't care what operating system is running them. We are focused purely on the semantics of the business, what things exist, what rules govern them, how they relate to each other. This approach kind of future-proofs the design. It lets the organization pivot to new technologies later without having to completely redefine their core business logic.
That makes a lot of sense. It's like designing the structure of the house before you worry about whether you're going to use wooden beams or steel
Yeah.
girders, right? Our sources lay out a pretty clear progression, that sort of funnel of design you mentioned.
Exactly. It's really a three-step journey from pure abstraction to actual implementation. Step one is where we are right now. Business ideas and requirements lead to the conceptual design, which we typically represent with the ER model. Step two, that's the logical design. This translates that ER model into a formal relational database schema, basically a list of tables, columns, primary keys, foreign keys. And then step three is the physical design. This takes that logical schema and implements it on a specific relational DBMS, optimizing it for performance on that particular hardware and software stack. Conceptual modeling is phase one. It's the intellectual heavy lifting.
Okay, so when we're doing this initial phase, what are the absolute core business questions that, if we leave them unanswered, pretty much guarantee a flawed database later on?
Yeah, we're hunting for information in three main categories. First, identifying the primary entities, those real-world objects or concepts, and the key relationships between them that make up the mini-world we're modeling. Second, figuring out the specific data points we need to store about those entities, which are the attributes. But the third element is often the most vital and honestly the hardest to capture perfectly. What are the mandatory constraints or business rules? This is where we capture the semantics. For example, the conceptual model has to state definitively whether a customer must have placed an order to exist in the system or if they can exist without one. Nailing down these rules now prevents so many painful data integrity errors later.
The main tool we use for this blueprint, the entity relationship model, it's incredibly popular. Why has it stuck around as the standard for decades?
Because it speaks the language of business, fundamentally, not the language of code, its core concepts, entities, relationships, attributes, they map very intuitively to how humans, especially business users, perceive the organizational landscape. When a manager talks about students enrolling in classes taught by professors, we can almost immediately visualize the corresponding ER diagram. And the enhanced entity relationship, or EER model, which we'll get into later, extends this expressive power even further to handle more complex stuff like specialization and inheritance.
So we've established the what and why, but how do we actually draw this thing? Because I know for students, the visual language, the notation itself, can add another layer of confusion when they're looking at different textbooks or software tools.
It definitely can, yeah. And understanding the differences, the trade-offs between notations, is actually part of that professional communication outcome, WO1. We primarily deal with three major approaches in practice. The original is Chen notation. It uses distinct geometric shapes, rectangles for entities, diamonds for relationships, ovals for attributes. It's conceptually very, very clear because it visually separates every single component. It's fantastic for teaching the underlying theory, really understanding the parts.
But then as soon as you get into industry tools, you almost immediately switch over to crow's foot notation, right?
Almost universally, yeah. Crow's foot dominates industry because it's much more implementation-focused and highly concise. Instead of using a separate diamond shape for the relationship type, it uses lines and symbols attached directly to the entity boxes. And crucially, it clearly emphasizes cardinality and participation right there on the connection line itself. That little three-pronged fork, the crow's foot, that indicates the many side. That's an immediate visual cue that tells you exactly how the foreign key is going to be placed when you translate its tables. It's just faster to draw, and it translates more cleanly to the logical relational model we need next.
And then there's UML.
Right. The UML class diagram is sort of the object-oriented cousin to ER diagrams. If an organization is heavily into software development, where behavior and data are often modeled together, UML is usually the standard. In UML, classes correspond pretty directly to ER entities, and associations map to relationships. It integrates data modeling with function modeling. But the key takeaway remains. The notation, whether it's Chen, crow's foot, or UML, is just syntax. The underlying semantic rules, the entities, the relationships, the constraints, those must be identical regardless of which picture you drew.
Okay, let's move past the drawing styles and dive into the actual components, starting with the core building block, the entity. Give us the definition and maybe clarify that important distinction between the abstract idea and the actual data sitting there.
Sure. An entity is basically any distinguishable real-world object or concept that has an independent existence. That word distinguishable is really important. Every single instance of an entity must be uniquely identifiable from all others. Think of a specific person, a particular invoice, or one unique product. When we're modeling, we define the entity type. That's the schema, the blueprint, kind of like the class definition in programming. For example, customer.
And the actual data, the records themselves.
That's the entity set, or sometimes called the entity collection. That represents the collection of all actual instances of that entity type that exist in the database at any given point in time. So if your database has, say, 10,000 customers right now, those 10,000 records make up the current entity set for the customer entity type. This difference matters because the entity type is relatively static. It defines the structure, but the entity set is dynamic. It changes every single time you insert or delete a customer record.
Okay, moving on to attributes. These are the descriptive properties of an entity, the details we actually need to store about it. And the values of these attributes, that's what forms the bulk of the data we store. Every attribute has to belong to a domain, right? Which defines the allowed values.
Exactly. The domain ensures data type consistency, like saying age must be an integer or hire date must be a valid date format. Sometimes domains also enforce value constraints, like age must be positive. We also categorize attributes based on their structure. The most basic distinction is simple versus composite. A simple attribute, like employee ID or last name, is atomic. You can't logically subdivide it further. A composite attribute, however, can be broken down into meaningful smaller parts. The classic example is always address, which you can decompose into street, city, state, and zip code.
Why does making that distinction matter way back here in conceptual design?
Because it forces you, the designer, to ask a critical question early on. Do we ever need to query, sort, or filter based on just a part of that attribute? If a business requirement says we need a report listing all employees living in the 76010 ZIP code, then address absolutely must be modeled as a composite attribute. That ensures zip code is individually accessible. If you just model it as a simple single-string address attribute, you make that specific query either impossible or incredibly inefficient, involving complex string manipulation.
Got it. Okay, the next distinction, single-valued versus multi-valued, seems like where the theoretical model and the practical relational implementation really collide. This forces a critical design decision, right? Part of SO2.
Oh, absolutely. This is a major stumbling block for new designers. A single valued attribute can hold, at most, one value for any given entity instance. Think date of birth, you only have one. A multi-valued attribute, theoretically, can hold many values for a single entity instance. Common examples are an employee's list of skills or a product's various available colors. Now, while Chen notation actually has a symbol for this, the double ellipse, you must never, ever try to implement a multi-valued attribute directly within a single column in a relational table.
And why is that such a hard and fast rule in the relational world? What breaks?
Because it fundamentally violates first normal form, 1NF. And 1NF is the absolute bedrock of the entire relational model. 1NF demands that every cell, every intersection of a row and column in a table must hold a single atomic value. No repeating groups, no lists within a cell. If you try to cram multiple values like red, blue, green into one color cell, or if you try to anticipate by creating multiple fixed columns like color 1, color 2, color 3 in the main product T table, you create massive structural instability. What happens when the business needs to track a fourth color? You have to alter the table structure. How do you easily search for all products that come in red? The query becomes needlessly complex and inefficient.
So the practical takeaway for BCIS 4301 students is immediate and non-negotiable. If the requirements analysis uncovers something that looks like a multi-valued attribute, what's the mandatory resolution?
You must resolve it conceptually, right there in the ER model, by creating a new entity specifically to hold those multiple values. This new entity, sometimes called an intersection or bridge entity, but let's just call it a related entity for now, will connect back to the original entity using a one-to-many 1M relationship. So, for example, the multi-valued skills attribute of employee becomes a brand new employee skill entity. One employee can be related to many employee skill records, one for each skill. This approach ensures flexibility. You can add unlimited skills without changing the employee table structure, and it adheres perfectly to the relational model principles.
Okay, good. Let's quickly touch on derived attributes.
Right. Derived attributes are values that can be calculated or derived from other stored attributes. They represent a critical efficiency trade-off. The classic example is age, which you can always calculate from a stored date of birth. The designer has a choice here. Is the calculation complex or time-consuming or frequently needed? If so, maybe we should physically store the derived value, like storing age directly. But that introduces redundancy and potential inconsistency. You have to update age whenever the current date changes, or if date of birth is corrected. Or should we simply calculate it on the fly whenever it's needed during retrieval? This saves storage space and guarantees the value is always current, but it might slow down queries or reports that need that derived value for many records. It's a balancing act.
Makes sense. Okay, to wrap up this section on building blocks, how do we guarantee that distinguishable part for every entity instance? This is where keys come in, right?
Exactly. Keys are fundamental for ensuring uniqueness. We start with the idea of a superkey. A superkey is any set of one or more attributes whose combined values uniquely identify each entity instance within the entity set. It might include more attributes than strictly necessary. Then we refine that to a candidate key. A candidate key is a minimal superkey, meaning it's the smallest possible set of attributes that still guarantees uniqueness. You can't remove any attribute from a candidate key without losing that uniqueness guarantee. An entity type might actually have several candidate keys. For instance, a student could potentially be uniquely identified by their student ID or perhaps by the combination of social security number and birth date.
And the primary key, PK, is the chosen one, the champion identifier.
Precisely. The PK is the one candidate key that the database designer selects during conceptual or logical design to be the official primary means of uniquely identifying entity instances for that type. We usually show it by underlining the attribute, S diagrams. When designing, we also think about internal identifiers, which use the entity's own attributes, like a product code, versus external identifiers, which rely on attributes borrowed from related entities via relationships. This idea of external identification is critical when we think about identifying relationship instances themselves, because a relationship instance doesn't really have its own intrinsic key attributes. It's identified by the keys of the entities it connects.
Okay, perfect transition. Let's talk about those connections, relationships, and the rules that govern them. Section 3, relationships and constraints, touching on KO2 and SO3.
Right. If entities are like the nouns in our data sentence, relationships are the verbs. A relationship defines some kind of meaningful association among two or more entities. Examples are everywhere. Professor Smith teaches course CS 101, or Customer Miller places order 500.
And just like entities, we have the abstract definition, the relationship type, like teaches or places, and the dynamic set of actual connections, the relationship set. The complexity also involves the relationship's degree, basically how many entity types are participating in that relationship.
Exactly. While the vast majority of relationships you'll model and implement are binary linking exactly two entity types, the conceptual model needs to be able to handle others. We can have ternary relationships involving three entity types, like a supplier providing a specific part to a particular project, or even higher degrees, though they become complex quickly. And then there are these structurally unique unary or recursive relationships.
Recursive relationships are always fun to diagram. Visually, they show an entity type relating back to itself.
Yep, they're essential for modeling hierarchies or self-referential structures. The classic example is the corporate org chart. An employee entity relates to another employee instance via a supervises relationship. Now, a critical rule here. Whenever an entity type participates in the same relationship more than once, maybe in different capacities, you must use role labels on the diagram. In the supervision example, you'd label the connections as supervisor and subordinate to clarify exactly which role each participating employee instance plays in that specific association. Without those role labels, the diagram becomes ambiguous and essentially useless for translation.
Okay, can a relationship itself have descriptive properties like attributes? When does something like start date belong to the association itself rather than to one of the entities involved?
Good question. A relationship attribute is only appropriate if the property describes the association itself, and it cannot logically or uniquely be assigned to any one of the participating entities alone. Take a membership relationship between an employee and a department. An attribute like start date probably belongs in the relationship. Why? Because the employee's overall hire date with the company might be different from the date they started working in this specific department. That start date only makes sense when you consider both the specific employee and the specific department together. This is often a strong hint, by the way, that this relationship might need to be elevated to become an associative entity later during refinement.
Okay, now let's get into the constraints. These are absolutely essential for defining the business rules accurately, which directly impacts SO3, applying database strategies. Let's start with cardinality ratios, the basic connectivity limits.
Right. Cardinality fundamentally specifies the maximum number of relationship instances that an entity instance can participate in. We usually talk about the general classifications first: 1.1, 1-to-1, 1-to-many, or MN, many to many. Now, it's important to remember that the 1M relationship is really the structural backbone of relational databases. It's by far the most common type and the easiest to translate directly into tables using foreign keys. The MN relationship is perfectly valid conceptually. It represents a common business scenario, but it must be resolved into simpler relationships before you get to the implementation phase.
But those general ratios, 1.1, 1M, MN, they don't capture the whole story, do they? We need more precision, especially for defining whether participation is required. That's where the min-max constraints come in.
That's exactly right. The min-max notation, often used in conjunction with crow's foot, is what truly dictates the precise business rule. For instance, if you have an employee works for department relationship, and the cardinality on the department side is shown as 1N next to the employee entity, that means an employee works for at least one department and potentially many. If the model allowed that, usually it's 111. This minimum value, the min part of min-max, immediately leads us to the second crucial type of constraint: participation.
Participation defines existence dependency, right? Does an entity instance have to be involved in this relationship?
Precisely. Mandatory or total participation means every single instance of that entity type must participate in at least one instance of that relationship. This enforces an existence dependency. The critical implication for implementation, and this connects directly back to SO1, writing SQL, is that the minimum cardinality is $1 or greater. If the business rule says every professor must teach at least one class, then the professor entity has mandatory participation in the teacher's relationship.
And the crucial implementation point here, just to hammer it home, is that mandatory participation translates directly into a physical database constraint, correct?
Absolutely. This is the direct bridge between the conceptual design rule and the actual SQL code. If participation is mandatory for an entity on the many side of a 1M relationship, or either side of a 1.1, the resulting foreign key, FK column in the logical schema, must have a not un-L constraint defined on it when you create the table. This not un-L constraint enforces the business rule at the database level. You physically cannot insert an employee record, for instance, without providing a valid departmented if their participation in the works for relationship is mandatory. If the designer forgets or skips this not un-L constraint, the business rule is immediately broken and you start getting data integrity problems.
Okay. Conversely, optional or partial participation means an entity instance can exist without necessarily participating in that particular relationship.
Right. In this case, the minimum cardinality is $0. An example might be a course entity in the university catalog. A course can exist conceptually even if there are no specific class sections scheduled for it in the current semester. Its participation in the is scheduled as relationship with class is optional. The crow's foot notation makes this very explicit and easy to read. The small circle symbol O, right next to the entity box, indicates optional participation, while the hash mark or vertical bar symbol indicates mandatory participation. Getting this wrong is a common mistake. For example, incorrectly marking a professor's participation in teaching as mandatory when they might be on sabbatical or doing research only will literally prevent you from entering legitimate data about that professor into the database.
Let's touch on some more advanced constraints, maybe focusing on relationship strength, because this seems directly related to how the foreign key behaves during implementation.
Yeah, relationship strength is particularly important when translating to the relational model, especially in how keys are passed down and whether that foreign key becomes part of the child entity's own identifier. A weak or non-identifying relationship is the most common scenario. In crow's foot notation, it's typically represented by a dashed line connecting the entities. This happens when the foreign key placed in the child entity, the many side usually, is not part of the child's primary key. It's just there for reference to link back to the parent. For example, a customer places an order. We put customer it as an FK in the order table to know who placed it. But the order table's primary key is probably just orderid. The customer it is purely descriptive or linking information in the order table. It doesn't help identify the order itself.
Okay, and the alternative is the strong or identifying relationship.
Right, shown with a solid line in crow's foot. This occurs when the foreign key migrated from the parent entity is a necessary component of the child's composite primary key. Think about an order and its associated order line items. A single order line item cannot be uniquely identified just by its line number, like line 1, line 2, etc., because multiple orders will have a line number 1. To uniquely identify a specific line item, you need the combination of the orderid, the FK inherited from the parent order entity, plus the line number. In this case, the orderid FK is identifying because it forms part of the child's composite PK.
And this concept of a strong identifying relationship connects directly to the idea of weak entities, doesn't it?
It does, very directly. A weak entity is one that is structurally dependent on another entity called the parent, owner, or identifying entity. A weak entity has two key characteristics. One, it is existence dependent on the parent. It cannot exist if the parent doesn't exist, AND2. Its own primary key is partially or totally derived from the primary key of the parent entity via that identifying relationship. The classic textbook example is the dependent entity related to an employee. A dependent, like a spouse or child, cannot exist in the employee database without an associated employee record. Furthermore, the dependent entity's identifier typically requires the employee's primary key, for example, employee ID, plus some attribute that distinguishes dependents within that employee's family, like dependent name or a sequence number, DEPNUM. Weak entities and their identifying relationships are a crucial concept for accurately modeling data structures where one thing is inherently part of or dependent on another. They often get special notation, too, like double-line boxes or relationship diamonds in Chen, or double-line boxes in crow's foot.
All right, moving beyond the basics of ER, let's get into Section 4. Advanced modeling, particularly the enhanced entity relationship, ER concepts, and the philosophy behind design choices. This covers KO2, KO5, and WO1.
Okay, so The Enhanced Entity Relationship, or ER model, gives us the necessary tools and vocabulary to handle more complex scenarios, the kind you find in large organizations, especially when dealing with classification hierarchies and categories.
We're talking about things like generalization and specialization here.
Precisely. Specialization is fundamentally a top-down refinement process. You start with a single, relatively broad entity type, which we call the superclass, like person, and then you define distinct subgroupings based on specific characteristics or behaviors. These are the subclasses like student, faculty, alumni. Generalization is essentially the reverse, a bottom-up process. You might identify several distinct entity types, say car, truck, motorcycle, that share common attributes and relationships, and you abstract those commonalities into a more general superclass vehicle.
And the fundamental mechanism driving this is the ISA hierarchy. Literally, a student is a person. This brings in the powerful concept of inheritance.
Inheritance is one of the biggest benefits of using ER modeling. The subclasses automatically inherit all the attributes, keys, and relationships defined for their superclass. So if the person superclass has attributes like name, address, and date of birth, then the student subclass automatically gets those three attributes. We only need to define the student-specific attributes, like major or GPA, at the subclass level. This promotes consistency, reduces redundancy in the model, and makes maintenance easier.
But just defining the hierarchy isn't enough. We also have crucial constraints that dictate how a specific entity instance fits into this structure. Like, can an employee be just one type, or can they wear multiple hats?
Right, that defines the disjoint versus overlapping constraint on the specialization. A disjoint specialization means that an instance of the superclass can belong to, at most, one of the defined subclasses. For example, in a simple biological classification, a person might be specialized into man or woman, but not both simultaneously in that specific model's context. It's an or condition. An overlapping specialization, however, means that a single instance of the superclass can belong to multiple subclasses at the same time. A very common example in a university database is a person who might be specialized into student and employee concurrently think of a graduate teaching assistant. It's an and/or possibility.
Okay, and then there's another dimension, completeness. Does every single instance of the superclass have to fall into one of the defined subclasses, or can some just be the general type?
That's the total versus partial completeness constraint. Total specialization means that every instance of the superclass must belong to at least one of the defined subclasses. There are no instances that are only the superclass type. For example, if we define that every single employee must be categorized as either full-time or part-time, that would be a total specialization. Partial specialization, which is often the default assumption if not specified, means that instances of the superclass may exist that do not belong to any of the defined subclasses. For example, if our person superclass in the university database is specialized into student and faculty, there might be other types of people recorded, like administrative staff, temporary contractors, visitors, who belong to neither the student nor the faculty subclass. They just exist as person instances.
So ER provides this richer technical toolbox. But now we have to confront what our sources call the art of modeling, connecting to WO. They stress that conceptual modeling isn't always black and white. There can be multiple valid designs that satisfy the same basic requirements. This is where the critical thinking really comes in, isn't it?
Absolutely. This is where experience and judgment play a huge role. The primary intellectual challenge often boils down to that fundamental triangle, deciding whether a particular concept in the mini-world should be modeled as an entity, an attribute, or a relationship. This choice has significant downstream effects on the flexibility, integrity, and even performance of the final database.
Let's revisit that address example we talked about earlier. We established it can be just an attribute of person. But when does it have to graduate to being its own fully fledged entity?
It really depends on how the business needs to use address information. If the business only needs to store the address of the person simply as a descriptive property, then keeping it as a composite attribute within the person entity is usually fine. However, if the business needs to track complex information about the address itself, think of a utility company that needs to track installation dates, connection types, service history, and potentially multiple occupants over time at a specific physical location, then the address itself becomes a central object of interest. If the address needs its own independent identifier, like a unique property ID, or if multiple other entities, like two different employees sharing a house or multiple service accounts at one location, need to link to the exact same physical address record to avoid redundancy, then address absolutely must be modeled as an independent entity.
Okay. And what about the line between modeling something as a relationship versus modeling it as an entity? Specifically, when does a many-to-many MN relationship need to become an associative entity?
This transformation is almost always triggered when the relationship itself needs to hold data. That is, when there are attributes that describe the association, not just the participating entities. This is most commonly encountered with MN relationships. Let's take the classic MN relationship. Student right arrow enrolls right arrow course. If we then realize that we absolutely must store the grade the student earned in that specific course offering, or the date enrolled, or maybe an audit status flag, these are all attributes that describe the enrollment event itself. They don't belong solely to the student, who has many enrollments, nor solely to the course, which has many students enrolled.
So the need for these descriptive properties on the association itself basically forces the resolution.
Precisely. The need to store attributes on the relationship is the strongest indicator. Therefore, the MN relationship must be resolved conceptually, usually by introducing an associative entity, sometimes called a bridge, junction, or intersection entity, before you translate the model into a relational schema. This associative entity, let's call it enrollment, then sits in the middle and acts as the hub. The original MN relationship is replaced by two new 1M relationships. Student has a 1M relationship with enrollment, and course, or more accurately, course section, as we'll see, also has a 1M relationship with enrollment. This resulting structure is perfectly relational compliant, and the enrollment entity provides the natural place to store those crucial relationship attributes like grade, enroll date, etc. If you try to skip this resolution step, your logical database design will fail immediately. There's simply no place to correctly store that data in the relational model.
Okay, this leads us nicely into Section 5, the iterative design process itself and the final conversion to a relational schema, hitting KO3 and SO1.
Yeah, it's really vital to stress that conceptual modeling is almost never a linear, one-shot deal. It's fundamentally an iterative process. You have to expect to start simple, maybe even with some ambiguities, and then constantly refine the model, checking it against detailed requirements, edge cases, and potentially evolving business needs.
The basic steps seem clear enough. Identify entities, then relationships, then attributes, define keys and domains, figure out cardinalities and participation, and finally layer in the more complex EER hierarchies if needed. But what kind of strategies do experienced designers actually use when they're building these complex models from scratch?
Well, designers can employ different approaches. A top-down strategy starts with a very high-level, abstract view of the main entities and relationships, and then progressively refines the model through successive specialization, adding more detail and breaking down components as more requirements become clear. Conversely, a bottom-up strategy might involve starting with several smaller, simpler schemas, perhaps representing different user views or functional areas, and then integrating these partial schemas into one comprehensive, unified model. In reality, for most large projects, professionals tend to use a mixed strategy. They might quickly identify the core, high-level entities, top-down, but then iteratively refine the attributes, constraints, and relationships in specific areas based on detailed analysis, bottom-up, constantly checking for consistency and integrating pieces. The defining characteristic, regardless of the starting point, is that continuous cycle of refinement against the documented requirements. You draw something, check it, find a problem or ambiguity, revise it, check again.
Let's maybe dive into a concrete case study to show why that refinement is so often necessary. We touched on it earlier, the potential pitfalls of overly simple assumptions in something like a university model.
Right. The initial, maybe naive assumption that students or professors often make is simply a professor teaches a course and a student enrolls in a course. If you model that directly, you end up with an MN relationship between professor and course, and another MN relationship between student and course. Conceptually, it seems plausible at first glance, but this model breaks down almost immediately when you try to represent real-world university operations.
How exactly does it break? What can it handle?
Well, consider this common scenario. Professor Smith teaches BCIS 4301 in the fall semester. But maybe Professor Jones also teaches a different section of BCIS 4301 in the same fall semester, or perhaps in the spring semester. The simple MN model linking professor directly to course cannot accurately track which specific professor taught which specific offering of that course. It also can't track the specific grade a student received for that particular instance of taking the course. A course, like BCIS 4301, is really an abstract description in the catalog. Students don't enroll in the abstract idea. They enroll in a concrete class or section that is offered at a specific time, in a specific location, or online during a specific semester, and usually taught by a specific instructor.
So the failure of that simple, intuitive model forces a critical refinement step in the design process.
It absolutely necessitates the introduction of a new entity, often called course section or class or scheduled course. Let's use course section. Now the relationships become much more accurate. A course, the abstract catalog entry, for example, BCIS 4301, generates many course sections. Example, BCIS 4301, section 001, fall 2024, MWF 9am. The relationships are now properly structured. A professor right arrow teaches right arrow a course section. This might be 1 and M if professors can teach multiple sections, or potentially M if team teaching is allowed, which then needs another associative entity. And a student right arrow in a right arrow course section, this is inherently MN, as one student takes many sections and one section has many students. That M enrollment relationship would then, of course, be resolved into an enrollment associative entity to hold the grade, date, etc. This iterative step, moving from the simple course concept to the more concrete course section, is absolutely essential to accurately capture the operational requirements of the university, like managing room assignments, tracking enrollment limits per section, handling different instructors for the same course, and recording individual student grades correctly.
Okay, so once we have this refined, solid conceptual model, the EER diagram, it eventually has to be translated into the actual tables that a database management system can understand and implement. This is the transition to the logical model, right? Hitting KO3 and SO1. The translation rules seem pretty systematic.
Yes. Thankfully, the translation process from a well-formed EER diagram to a relational schema is quite systematic, though there are still some design choices, especially with hierarchies. The basic foundation is straightforward. Every regular, strong entity type in your EER diagram becomes a table or relation in the relational schema. The simple attributes of the entity become the columns of that table, and the designated primary key of the entity becomes the primary key of the corresponding table.
Simple enough. What are the relationships? How do they translate?
For 1M one-to-many relationships, the standard approach is optimized. We do not create a separate table just to represent the relationship itself. Instead, we place a foreign key, FK, in the table on the many side of the relationship. This foreign key column references the primary key column of the table on the one side. So if Department 1 employs Professor M, the professor table gets a new column, say dept code, which will store the primary key value of the department that professor belongs to. And as we discussed earlier, if the professor's participation in belonging to a department is mandatory, that dept code FK column must be defined with a not null constraint.
Okay, and what about those MN many-to-many relationships that we resolved using an associative entity?
Those resolved MN relationships, represented by the associative entity, like our enrollment example, translate directly into their own dedicated associative table in the relational schema. The primary key of this associative table is typically, though not always, a composite key formed by combining the primary keys of the two or more entities that participated in the original MN relationship. So the enrollment table's primary key would likely be the combination of student num plus class section name. This composite key naturally enforces the business rule that a specific student can only enroll in the same specific class section once. Any attributes that were placed on the associative entity in the ER diagram, like grade and roll date, become regular columns in this associative table.
Finally, let's revisit those ER concepts, specialization and generalization. How do we map that potentially complex inheritance hierarchy of subclasses and superclasses into the flat structure of relational tables? This seems like a place where the designer has some significant choices to make.
You're right. This is a core design trade-off with several established mapping strategies. The designer has 3 main methods for implementing an ISA hierarchy, and the best choice really depends on factors like query patterns, performance requirements, and tolerance for data redundancy or null values. Method 1. Separate tables for superclass and each subclass. In this approach, you create one table for the superclass, for example, employee, containing its common attributes and PK. Then you create a separate table for each subclass. EVRG hour lamps, salary tables. Each subclass table includes only its specific attributes plus a foreign key that is also its primary key, referencing the superclass table's PK. Trade-off. This method generally minimizes data redundancy and enforces integrity well. However, if you frequently need to retrieve all information about an employee, both common and specific attributes, you'll always need to perform a join operation between the superclass table and the relevant subclass table, which can impact query performance. This is often considered the cleanest logical approach, though.
Okay, method 2. Only create tables for the subclasses.
That's the second option. Here, you don't create a table for the superclass employee itself. Instead, you only create tables for the leaf-level subclasses, hour limps, salary demps. Each of these subclass tables inherits and duplicates all the attributes from the superclass, name, address, hire date, etc., in addition to its own specific attributes. Trade-off. This approach eliminates the need for joins when you're querying data specific to one subclass type, which can be faster for those queries. However, it introduces significant data redundancy. Common attributes are stored multiple times. It also makes schema changes much harder. If you need to rename the address column, you have to modify it in potentially many different subclass tables.
And the third way, method 3. Use a single large table for the whole hierarchy.
Right. Method 3 involves creating just one single, potentially very wide table for the superclass, person or employee. This single table includes columns for the primary key, all the common superclass attributes, and all the specific attributes from all possible subclasses. Trade-off. This method can be great for queries that need to aggregate or search across the entire population, all employees regardless of type, because no joins are ever needed. It can be very fast for such universal access patterns. However, it often wastes considerable storage space because many columns will be irrelevant for any given instance and must be populated with NL values. Example, a salaried employee row will have NL values in all the columns related to hourly wage, overtime rate, etc. It can also complicate data integrity checks due to the prevalence of these nulls.
So it sounds like method 1 prioritizes data integrity and flexibility, but might cost you in query complexity with joins. Method 3 prioritizes fast universal access, but costs you in storage space and dealing with NLLs. Method 2 is somewhere in between, but suffers from redundancy. Making that structural decision based on how the EER concepts map to tables seems absolutely vital for the eventual physical performance and maintainability of the database, touching on SO3 again.
Exactly. That mapping choice is a perfect example of how decisions made during logical design, informed by the EER model, directly impact the physical implementation and its long-term success.
Okay, let's try to wrap this up and summarize.
Right, let's summarize the sheer scale of what we've actually covered today. We started with that simple yet profound reality that databases really do run the modern world, and we mapped that reality back to the foundational blueprint, the entity relationship model. We carefully defined the core building blocks, entities, attributes, relationships. We established the absolute necessity of resolving things like multi-valued attributes and many-to-many relationships before implementation. And we explored how the enhanced ER concepts like generalization and specialization give us the power to accurately model complex organizational hierarchies.
And mastering this conceptual modeling process, it really is the essential bridge for anyone looking to build a career involving data or digital systems. It's what ensures that before you write even a single line of SQL code, SO1, your fundamental data structure is sound and truly meets the complex needs of the business, WO1. Trying to skip this step, or maybe getting the cardinality or participation constraints wrong back in phase 1, well, it's like trying to build an incredible skyscraper on a foundation made of sand. It's just not going to hold up. A solid conceptual foundation, clearly defined using the ER model, is probably the single best guarantee of a successful, robust database implementation. And it's definitely a core skill expected by employers, and certainly within the Dr. Sampat College of Business curriculum.
Based on our discussion today, you should now be in a much better position to explain the fundamental role these database systems play, KO1, to actually apply these robust data modeling techniques like ER diagrams, KO2, and importantly, to understand the real-world implications of your design choices, connecting these concepts to actual business problems and applications, WA1.
Absolutely. And remember, everyone, please follow the show, share it if you found it helpful, and definitely check out those extra resources linked in the description, especially the links that might clarify the specific syntax differences between crow's foot and Chen notations if you're switching between them. Now, for our final reflective question to leave you with, if the databases underpinning your daily life completely vanished tomorrow, everything from the university systems tracking your courses and grades, to the inventory systems managing food supply chains, to your streaming apps, which part of your routine would stop working first? And maybe think about what key ER entities and relationships would be missing that would prevent that system from ever recovering. Just consider that underlying complexity.
Behind every login, every swipe, and every single purchase, there's a database making it all possible. Until next time, keep exploring the world behind the data.